right? What's unique about this is that we have all the flight schedules in all the airlines all over the world. So basically, you can find combination where other engines can't, because we can combine also the airlines which are not cooperating. Okay, so the data. Of course, we have the data which goes to the search engine, and also we have the data which goes out, like search results. We store it, but I'll be talking more about the data generated after the customer chooses the flight. There is also a booking process. The customer will get to the booking page and he start paying and doing stuff, and we need to log these activities. We have a mobile app which is like logging activities, and also the booking page generates some logs. So this solution is for storing the logs, actually, front-end logs and logs from a mobile application. Why do we need logs from front-end or mobile application? When there is a customer on the phone and he's talking, I'm trying to click this button and it's not working, and something like that, the customer can just see all the things the user clicked on our website, or if he tried to pay, or something else, what he's actually doing in the mobile app. So we have decided to store all the data to the Postgres, and when it's like too much, we will switch to another solution. Currently, it's about 5 terabytes of data in the Postgres database, and the thing is that it wasn't reliable enough. There were like outages, 2 outages per week for 1 hour, for example. So we were losing the logs. So the problem was that maybe I can, this is the old code. You can see it's very simple. It's just this endpoint, store endpoint, and it was just storing the data, inserting into the Postgres. So once the Postgres was down, or the data center where the storage was running was down, it wasn't just working. This endpoint just return error code, and nothing has been stored. So you just need to think about other solution, which could handle also like storing a few records per second, which can handle slow database, and also which will be scalable for like many times than the traffic is now. Actually, I need to mention that when I came to Kiwi.com 2 years ago, we were just a bunch of 20 developers. Now we have 800 people in the company. So we are like one of these rocket scaling startups, and so we learned that we can't write code this way because it's not much scalable and it doesn't necessarily do the reliable thing. So that's the design of the system, which could possibly handle the outages of the Postgres. We have a mobile app and the front end, which is generating the logs. Then we have decided to use Kafka. Like, you probably know what's Kafka. It's a streaming platform, and I'll just use it like a pipe. I'll just put some data from the endpoint to Kafka, and on the other end, I'll just consume it from the Kafka and store it to the Postgres. The Kafka is heavily distributed, so it's really reliable. I think LinkedIn has developed Kafka, and there's other enterprise companies which is using it. So Kafka is like the reliable thing in this system. Postgres is not. And I'll show you the code which just takes the data, put it into Kafka, consume it from the Kafka, and store it in the Postgres, but not one by one, but in bulks to make it efficient. Okay, I have a note here, time to kill consumer. Okay, consumer is this part. I said it should be reliable, so let's kill it. This is our running consumers on our 3 servers, like in production, so I'll just stop it. This solution is Dockerized, actually. So we can use Rancher. This is the tool you can see on the screen, which handles all the running Docker containers. Like I don't need to type any commands to stop the servers. And there is some monitoring. On the black graph, you can see how many records have been received. Like on the endpoint. So received is what we received here, and here is what we store, right? So this is what we are receiving now, and this is what we are storing. It's like balanced, it's okay. And we'll see soon what happens when I stop the consumers. See, I stopped storing the data now, but I'll give it some time. So now the Kafka queue is like filling with the data, which is coming to the producer, but we are not consuming it. So, code samples. For those who are new to asyncio, I have prepared an example how it looks like and how it behaves. This is actually old code, but you can see it on the internet tutorials. In the Python 3.5 and later, this is not necessary because we have new syntax. This is like a modern way how to use asyncio. And the point is that we can just create a loop and put some task to the list. This code, it's not actually running the factorial method up there. It's just generating futures. It's like a special data type, you can imagine. And once we run the loop, it's run not in parallel, but it looks like it's run in parallel. That's what I like about asyncio. And here you can see here the output. So how does it work? Once we are sleeping there, the other futures runs, other instances of the same method. So it's no threading, it's no processes, it's like concurrency stuff. It looks like it's running parallel, but it's actually not. It's just switching the context. So this is the point of the concurrency and the Kafka asyncio. Okay, so you basically know how it works. You just put some task into the queue, and when the loop is running, it's just running. It looks like it's running parallelly. So, what we have used? Once we are using asyncio, we need to use a special module for it, like aiopg. And also, we have used classic JSON. In our company, we usually use UJSON because it's usually faster, but it doesn't work with asyncio well. We haven't figured out what's the problem actually, but it wasn't stable enough. And there is also other modules I'm using for consumer. Of course, Kafka. And this is the asyncio version of storing something to Postgres. Okay, I totally forgot I have switched off the consumer, so we'll check the graphs, what's happening. Oh, this is interesting. I expected this to be like 0, but it actually increased. I'll give it some time. But we see now the data we are receiving, it's delayed. So, how does the code of the producer looks like? We can see we have the store endpoint, like the same like in the old code, which is doing the only thing. It's receiving the data from the post request, and it's sent the same data to the Kafka. This is the send function. We'll just create a message, which is the data we have received, and also the timestamp. It is important to just store the timestamp of the time when we receive the data, because otherwise, sometimes, like when I stop the consumer, the data are in the queue for some time, and we don't care about the time of storing the data, but time we're receiving the data, because it's near the time it's generated. You can imagine the example when the database is down for like a day, and we want to have the data timestamp in the moment they are generated on the client side. So we are not actually, we are using the Kafka modules, but we are not having any benefits for the asyncio stuff here. And that's actually all the code, just receiving the data and putting it into the Kafka. One thing is, there is a one cool thing. When there is a Kafka error, which is not happening, it shouldn't happen, I need to like react somehow. I should like reconnect to Kafka possibly, or what I'm doing, I'm destroying all. It means I'm trying to exit from the process and exit the process. You can't do that if you are into the loop, as I understood. It's if you are trying to exit like this way, it won't work unless you stop all the tasks in the loop. This is what you need to do before. Get the loop, cycle for like among all the tasks, cancel them, then you can stop the loop and close it. Okay, I'll check the consumer again. This is really strange. I rather switch it on again. Fine. So, now the consumer part. We actually have two different flows which will run in parallel way. So, let's say we are starting together. At first, the right algorithm connects to the database. What's the left one is doing? He'll just waiting if it is connected or not. So we will need some synchronization between the right one and the left one. So once the database is connected, it goes to the yes, and it just starts receiving the data from the Kafka and put it into the local queue. Once the local queue is full, it will be stored to the database. Right? When I created the first version of this, I had a problem when there was a low traffic. The local queue was full like in a minute, let's say, and it makes the data stored to the database in really great delay. So there is actually two constraints. The queue needs to be full enough. It means at least, let's say, 10 records to be bulk stored in the database, or if it is old enough, it means at least 2 seconds in the queue. These conditions are like a yes. They can be stored to database. Before I'll show you the code of the consumer, I'll check this again. Oh, so when I run the consumer again, it looks like something has been in the Kafka queue, because now we are storing a lot more data than before, and also the delay is like getting better. fine. So this is the second slide about consumer, and I'll make it bigger. What? So this is the left part of the graph. It's consuming, like getting data from Kafka, and once we have consumed like enough of data, we will flush it into the database, right? So this is about consuming. We'll just connect databases. We'll create the async aiopg. I call it batch, and I will have two tasks: consume and flush. See, I'm ensuring future consume and another future start flushing. This is our consume and flushing processes. And once I have planned it, I have created the futures, like I know what I'm going to do, I'll just run the loop forever. It means it will be run in parallel without any end. And this is how the consume method looks like. I'll just connect to Kafka, start it, and I'm cycling on the consumer to get the data from Kafka, and every record I receive, I put it in the local queue. So it was the left part. And the right one. So the left part was just about getting data to the local queue, and the right is about waiting for the queue to be full enough and put it in the database. So we have start flushing method, which is just doing that it starts the keep flushing. And when the keep flushing somehow breaks, it will run it again. See, while true, and we are just running keep flushing. Okay, so what the flushing actually means, this is the condition on the right side of the previous slide. When the queue is big enough, it means it's bigger than some setting, or the timestamp of the last store time is like, if the queue is old enough, I'll just put the queue to the to-store structure, and I bulk store it into the Postgres. It's just insert, it's multi-insert. It's basically just having the queue, putting it into Postgres. There is just one thing, exception. When the database is down, it will just finish this while cycle, and it will be run again. So the database will be reconnected, and it will try to store it again. The great thing is that you can see it's like completely different pieces of code which share one structure, the queue, and it looks like it's running in parallel, but it's actually just switching the context. When I am, for example here, when I'm storing something to the database, the other part, like for example consuming something from Kafka, it can do it like in the same time. Like I'm waiting for the Postgres to store the data, so I have nothing to do. So I'll just switch the context and consume some more data from Kafka. That's what I, as a developer, don't care about that. The Python do it or async I do it. What I need to do is to describe the problem. Okay, let's check the graphs again. If everything is normal. It's not normal. Somehow we have a lot of data to store. It's kind of unexpected. What I expected was when I stopped the consumer, there should be a huge drop to 0 because we were not storing anything. When I run it again, there should be a peak. But why it's peaking now? Anyway, usually it works like expectedly. So that was all the showcase. We have a system which can handle the database down. Once the database is down or the consumer is down, the data are stored to Kafka. And also, it's a good example of having like parallel tasks which are like just concurrent tasks. So question time. Yep.
Thanks for the presentation. And how do you test it if ever when you develop it? How do you test it? This is a fairly complex system. How do you ensure that you don't break it when you introduce some change, and especially if it affects multiple points?
Yeah, I have some test data, and I have just run the test data over the old code and checked how it has been stored, how much of if the stored records were the same as the records received in the consumer part, and the same data I have just put through the new system, and I have seen, okay, it's like the amount of the records is the same and the characteristics of the data is the same. I said, fine, it works. And the thing which I have showed you, like stopping the consumer, that's another test. That's actually why I did it, to be able to like get over the database down status. So there is no like testing. I haven't spent testing much, like one day of just trying to simulate the situation when the connection is down, when the database is down, when the Kafka is down. But actually, when the Kafka is down, it doesn't work.
It will be if be laid down for a long time. Kafka,
Yeah.
for all data that your customers send it.
I have tested it for 6 hours of the downtime of the database, and Kafka is actually persistent, so it can store the data to the disk if needed. So it depends on the size of the disk, and since our data is like gigabytes per day, it's like easy to just put more disk to the Kafka. So our DevOps guys have some alerting, and if the queue is too huge, they will just add the more disk in the same time. So I don't need to do anything. It's yeah.
Okay, and what if your database is working again, and you send a huge amount of data that was in Kafka, and maybe something problem in this transferring huge amount of data?
Actually, I've tested this solution for a huge amount of data. Like, we can show the old code. And yeah, this is the old code. This code was able to handle like maybe 30 records per second. It's not much, because it's committing after every insert. And the new solution just wait for data for like 10 or 100 of the records and store it in one huge insert. So it's like almost 10 times faster, and it's customizable, like the batch size. And I have tested it for 40 times faster or 40 times huger traffic, and it worked. So I said, okay, 40 times is like good enough, and the database could handle that once it's not down, of course. Yeah, one thing. All the code you have seen on the slides is here. It's public and it's runnable once you have Kafka somewhere running. The Kafka is not part of this code, but if you have some Kafka running, you can just run this code on it, and it should work. It's a really simplified solution. It's like 80 lines of code. Yeah, this is me, this is our company, and this is our jobs. If you're interested, go there, or I'll be there like the whole day, and on after party you can just ask me about all the stuff you can see now about the code, me, or jobs. Cool.